Welcome back to this course on models of quantum computation, and we are now moving towards the topic of our lecture. So up to now it was mostly general review, quantum algorithms, the adiabatic model, and so on and so forth. And today, we're not moving quite to our first computational model yet, but we will work on a technical ingredient. We will present a technical ingredient, and that's the stabilizer formalism. So there will be two formalisms that we will discuss in this course today in the next couple of lectures. The first, stabilizer formalism, and then tensor networks. Okay, so let's get started with that. So here's an outline. Stabilizer formalism, I already said. So quantum processes are built from state preparations, unitary transformations, measurements, and some of those all of those will have a representation in our formalism that we are going to discuss, and for a restricted class of such operations, there will be a very effective, efficient description. So then we have a bunch of things to talk about. It's the Goddard-Monod theorem. It just talks about the efficiency of the description of these operations. Quantum error correction is very closely tied to the stabilizer formalism. This is not a lecture on quantum error correction, but we will review it briefly because it makes us appreciate the model of quantum computation with magic states. So I think for intuition, it's good to talk a little bit about it. And that has a particular aspect that will mean nothing to you right now, but it is in fact crucial. Yeah, it's called non-Clifford transversal gates in stabilizer codes. Whatever these words mean, we will talk about that. It's actually a fairly curious thing and important. Without this, fault-tolerant or quantum computation would be in trouble. It's a very important property. Okay, we will get to it in time. It's not the outline for today. So the stabilizer formalism has a lot to do with Pauli operators. So let us review Pauli operators. Okay, here are the Pauli operators for an individual or two-level system. Yeah? Sigma x, sigma y, sigma z. And you are familiar with those. And so they are with respect to a specific basis, namely the eigenbasis of this guy. And yeah, if we choose that basis, we call it the computational basis, then yeah, all these Pauli operators take this form. So we will have to write down a lot of Paulis in this course, and therefore we simplify the notation a little bit. So sigma x becomes x, sigma y becomes y, sigma z becomes z. So we leave out the sigmas, means the same. And so now we need to talk about multiple systems. So not just about one qubit, one two-level system, but many, any number. And then there are Pauli operators for these systems as well, and they are simply tensor products of local Pauli operators. So we can build them using the tensor product from what we had on the previous slide. So just one example here for two qubits. x1 tensor x2 is a valid Pauli operator on a two-qubit system. Another fact about Pauli operators, they either commute or anti-commute. So you can verify this in the spin 1/2, one qubit example. So among the three Pauli operators x, y, z, they are all pairwise anti-commute. The identity is also a Pauli operator, and everything commutes with the identity. So you have these two behaviors right there, commutation and anti-commutation, and you have nothing else. It's all that can happen. So this extends from the one qubit case to the n qubit case for any n. Pauli operators form a group. Yeah. So if P is a Pauli operator and Q is a Pauli operator, then the products PQ and QP are also Pauli operators. So just to kind of elaborate on this a little bit. So x, y, and z are Pauli operators. Products are Pauli operators. So the product of f of x and y is IZ. So is IZ, so Z is a Pauli operator, IZ is a Pauli operator, Z is a Pauli operator. So I, the imaginary unit, times the identity is also a Pauli operator. So this is something to take care about. Some Pauli operators are just phases, powers of I. Good. Okay, so also this means that some Pauli operators are Hermitian, but if we look at the Pauli group, not all Pauli operators will be Hermitian because of these phases. Yeah, sometimes we have to take care of that. Okay, so this was it. So this was the recap from last couple of times. And now we begin. We begin with the simplest example of a stabilizer state and the stabilizer description. And then there's a few questions. I mean, it's a silly example, but we will build from there. Okay, so so this state here plus is the eigenstate of the Pauli operator X, and if we write it in terms of the eigenstates of the Pauli operator Z, it takes this form. So we know that well. Nothing new here. So, but it is the eigenstate with eigenvalue +1 of the Pauli operator X. So we write this down, and this is just, it's not just a property of that state, it's also the defining property. From that relation, we get that state modulo a global phase. And global phases we don't care about. Yeah? So global phases have no physical meaning, no observable effect follows from them. Relative phases, yes. So a completely different beast. Okay, so from this relation, we get that state modulo global phase. Yeah, so it's an equivalent definition of the state. We can define it like this, we can define it like that. This is the route we want to follow. So this is a stabilizer relation. We will later call it a stabilizer relation. So we have a state that's an eigenstate of a Pauli operator. So if I have sufficiently many Pauli operators for which I find such relations, then this uniquely defines my state. In this case, the one qubit example, I just need one of those operators. Okay, so now at this super early stage, we haven't even defined what a stabilizer is properly, but at this early stage, we already try to build an intuition for what's going on. So, so tell me, now we have the tensor product of n eigenstates of x, so eigenstates of x1, and so forth, and so forth. So, and I, like up here, I expand this in the computational basis. How many terms do I get? Yes, it is 2 to the n. Yeah, you get for each qubit, you get an expression like this, and then you multiply it out, and it's like a polynomial. You get 2 to the n terms. Yes. So let's write it down. So the answer was 2 to the n. Okay, and so now next question: how many constraints of this type here? How many such constraints must I write down to uniquely define this state? Tensor product of all these pluses. How many? It's the other question. N, yeah. That is the correct answer. And why is this? Well, the relations are like this. We have x1 applied to that state is that state. x2 applied to that state is that state. x3, yada yada, until xn. So n such relations. This is correct. And so, I mean, this is a toy example. You were not, I mean, there's nothing special so much about the computational basis, and there are other local bases in which the number is smaller. But it gives you the general idea. So typical quantum states, if you want to write them down in any basis of your choice, you'll have 2 to the n coefficients, because that's the Hilbert space dimension. Okay, but if you are dealing with a stabilizer state, and most states are not, you only need n constraints to write them down. To define them, excuse me, you need to write down n constraints to define those states. So that's efficient. So efficient in the number of qubits, inefficient in the number of qubits. So here you see kind of the good and the bad of the stabilizer formalism. The good thing about it is that when it applies, it is efficient, but it rarely applies. That's the flip side, but it applies in important situations, as we will see. I mean, error correction is formulated in the stabilizer formalism, so there are important applications. So let's write this down. Stabilizer formalism is efficient where it applies. Yeah, so that's the flip side. Okay, so that's kind of an idea that we are getting at. This is just a hunch right now. We haven't even written down anything about the stabilizer formalism. I mean, except these examples. But that's the content of the Goddess-Manil theorem. So the efficiency of the stabilizer formalism, when it applies, has a theorem dedicated to it, and it's called the Goddess-Manil theorem, and we'll get to that. An example of interest. So this example that we just had was a toy example, just to make this point about efficiency. But here is an example of interest, namely the Bell state. So let's take the spin singlet. That's a state that's written down up here. We are quite familiar with it by now, and it is a stabilizer state. So tell me what stabilizer elements you can find. Oh yeah, what is a stabilizer element? A stabilizer element is such a thing here. Let me see. I should say stabilizer operator. What it is an element of, we'll get to very shortly. I should say stabilizer operator. So tell me, what stabilizer operators do we have here for that state? Yeah, so what the stabilizer operator is supposed to do, when I apply it to the state in question, it should leave that state unchanged. The state in question is an eigenstate of that thing with eigenvalue 1. Okay, here in my case it's called ZA cross ZB. Sorry, my fault. And is that it or what? Should be minus, yeah. Okay, and that is now correct. Does this define the state uniquely? No. Okay, so we keep on looking for other things. Okay, let me write that down. XA tensor XB, excuse me, B11 is B11. Same question as before? Minus sign again. Yeah, is this now complete? Yeah, okay, we have no proof of this yet, but it will follow from what we do. So the number of independent stabilizer relations is always the number of qubits. So this uniquely defines the state. It is also a very physical description. I mean, if you remember when we talked the spooky action at a distance thing about Bell states, yeah, measurement here of one particle projects the state of the other particle, no matter how far these particles are apart. So this works because of the quantum correlations between the two parties. And so the stabilizer describes the quantum correlations in the state. So it's a very physical description. So the upper half of the slide is just what we had. And so now you can either derive it or just check it. This is not all the stabilizer relations that there are. So this guy, minus YA times YB, is also a stabilizer operator. If you just kind of work it out, you'll find if you apply this operator to this state, you also get the state back. And as it happens, and that's not a coincidence, this operator here is the product of those two. Yeah? And so we are getting a hunch here that the stabilizer is a group. So that's why I was saying element. I was alluding to the group really before introducing it, and we will later prove it. So the stabilizer operators form a group, and that's called the stabilizer group. Another thing that we observe is that these operators here commute. Huh? So, I mean, if we look at these operators locally, we have anti-commutation, but we have anti-commutation twice. First particle, second particle, always xz anti-commutation. So overall, we have commutation. Okay, so get a hunch. Maybe the stabilizer is actually an abelian group, and that will turn out to be the case. Good, so we can see this here working in our first example, and it will hold in general. Okay, then let's move on. So I hope the example has given you a little bit of an idea of what we are talking about. And now we make the formal definition. So what do we have here? We have the definition of what a stabilizer state is and what a stabilizer group is. So whenever we have important definitions, I try to typeset them just that they are more easy to read. Okay, so all right, so by now we are familiar with the elements of this definition. So this is our stabilizer state, and it has a stabilizer. The stabilizer is a bunch of operators, bunch we will define in a moment, such that when we apply an operator from that set to that state, we get the state back. That is, our stabilizer state is an eigenstate of that operator with eigenvalue +1. Okay, so that is the first part of the definition, and I want sufficiently many such operators such that all the resulting constraints uniquely define that state, or define it up to a global phase that has no physical significance. Okay, so that is what a stabilizer state is, and now we talk a little bit more about the structure of that set curly S. So that set curly S is actually a group, and it is a subgroup of the n-qubit Pauli group. That is not very surprising because these are all Pauli operators. It is an abelian group, so everything in this group pairwise commutes. It is maximal, that is, we cannot extend it, we cannot make it bigger and preserve all these beautiful properties. And the last property is that minus the identity is not in the stabilizer group. So I have formed a shopping list of all these properties here that we are now going to show. Yeah? So we already saw it in the Bell state example, but we are now going to demonstrate them. So there is one more thing that's also on this list. It doesn't appear in the definition here, but it is important, and I will say why later. But if we are dealing with qubits, then all of these operators are also Hermitian. All the stabilizer operators are Hermitian. Good. Okay, so let's go through these properties. So we'll go through them in a somewhat different order. Okay, so let's see. So we begin with the property that minus the identity should not be in the stabilizer. And so we do this as an indirect proof. So we assume the opposite. We assume that minus I is in the stabilizer. Okay, so let's see what then follows. So we have a state psi, and that is also minus I times psi, because by our assumption of our indirect proof, minus I is in the stabilizer, but this is nothing but minus psi. So now psi equals minus psi, and that's very constraining, so this means that psi is the null ket. And that's not something that we want, that's not a proper quantum state. Okay, contradiction. So our indirect hypothesis is wrong, and so we are done with this first little proof. Minus the identity cannot be an element in a stabilizer group. Good, what is the next thing? So Hermitian. So, and I should say at this point, so later we will also look at systems with more levels, and then hermiticity will not apply anymore. And if you have 3 or 4 level systems, it will not apply, but for qubit it does apply. And we are getting some mileage out of it, and so I will mention it. So, okay, so suppose a Pauli observable P or Pauli operator P is in our stabilizer group. So this means that the square of it is, oh gosh, we have not shown the group property yet, so I have to show that. But it means that that P squared is also in the stabilizer. And we know from just a Pauli multiplication table that depending on what phases are in here, the square of Pauli's is, it's always proportional to the identity. The proportionality constant can differ, but it will always be proportional to the identity. Okay, so that we know, and we find that this will be in conflict to P squared being in S. But so let's just first show that P squared is in S. Yeah, so let's show that thing. So we have P squared psi is P psi, just by associativity, which is P psi, which is psi. Okay? Just using associativity of multiplication here. Okay, so if P is in the stabilizer, so is P squared. But P squared is proportional to the identity, and so now we have 2 cases. Case A, P squared is 1, so that's okay. But then it follows that P is Hermitian. Yeah, so if the eigenvalues of, if P squared is the identity, then the eigenvalues of P squared are all +1. This means the eigenvalues of P are +1 -1, which means that it is Hermitian. Okay. So the case B is P squared is not the identity. So it's the identity up to some factor. And then an argument like this kicks in. Yeah? So we don't have to have this factor to be -1. It can be anything but +1. Yeah? So the argument would still go through, and that is what we are using here now. So if P squared is not the identity exactly, then this is a contradiction to P being in the stabilizer by what we had before. And P is not in the stabilizer. Contradiction. So this is what we remain with. Okay. And why is this important? This is important because, remember, Hermitian operators are precisely the operators that can be measured. In quantum mechanics, observable quantities correspond to Hermitian operators. Yeah? And so stabilizer operators can be measured, and that's exactly what we're going to do a lot. In quantum error correction in the stabilizer formalism gets by measuring stabilizer operators. Yeah? So this is an important property. Then let's move on. So what do we have next? The group property. Okay, so we want to verify that if P and Q are in the stabilizer, then so are the products. Okay, so let's do that. PQ psi, that means similar argument, is, let's see what this is. So this is PQ psi equals p psi, since q is in the stabilizer, equals psi, since p is in the stabilizer. Okay, so pq is in the stabilizer. Okay, so the other is the first thing that we had to show. The other thing we have to show is that p to the minus 1 is in the stabilizer. So p to the minus 1 is, since p is unitary, p dagger, but since p is Hermitian, this equals p. So p is already known to be in the stabilizer, so p to the minus 1 is also in the stabilizer. And that's essentially what we have to require of a group. Oh yeah, what else? I mean, we have the identity. The identity also has to be in the stabilizer group. Yeah, so this is the third property. Identity is in the stabilizer. Yeah, and it's kind of obvious. Yeah, so that holds for all states psi, in fact. Okay, good. So it is a group. It's in fact an abelian group. So everything, I mean, Pauli operators can commute or anti-commute, but if they are part of the stabilizer, then they must commute. In the stabilizer, they cannot anti-commute, and let's see why this is. Okay, so let's assume that P and Q are in the stabilizer, and they anti-commute, yeah? So assume not, so we've, sorry, I should have written this differently. So if it's not an abelian group, then there exists P and Q such that PQ is minus QP, yeah? So Pauli operators can only commute or anti-commute. If they do not all commute, I can always find such a pair. Okay, so this is my indirect assumption in this proof. So let's go with that. But still we want P and Q to be in the stabilizer. Okay, so we find psi is Q psi equals QP psi. Yeah? Just kind of use the stabilizer relation twice. Now I'm using anti-commutation. So this is minus PQ psi. Yeah, and now I'm pulling these operators back. So this is minus P psi. Yeah, so I've used the stabilizer relation is minus psi. Use the other stabilizer relation. Yeah, so it was P and Q are both in the stabilizer. Or I should say P and Q in the stabilizer. That's too messy. Yeah, okay. And so that's again a contradiction, yeah? So psi equals minus psi means psi is the null ket. It's not what we want to talk about. Okay, so indirect assumption is wrong, so S is indeed abelian. Good. Okay, final property, maximality. Yeah, we said it's a maximal abelian group, and maximal means we cannot add anything to it without breaking the properties that we wanted. Okay, so assume it's not so. So this means there is a Pauli operator that we can add such that this Pauli operator commutes with the stabilizer, but it is not in the stabilizer. Yeah? Neither itself nor minus itself is in the stabilizer. And so we can now form two stabilizer groups. One is generated by the stabilizer we so far have, and P, and the other one is generated by the stabilizer we so far have, and minus P. But these stabilizers stabilize different states. Yeah, so they do not describe the same state. And so that's what we wanted. We wanted a stabilizer group to describe one state and one state only. Good. Okay, so they must be maximal to do that. Good. Okay, so this is, I think, it for the definition of stabilizer states and groups. And with this, we would be done with the states. And now come the operations on the state, like unitaries and measurements. In the stabilizers, we do not have phases. Yeah, if P is in it, then the negative of P is not in it. Okay, and these operators are Hermitian, we said, in the stabilizer group, not in the Pauli group, but stabilizer. So they square to the identity. So now tell me, what is the group for an n-qubit stabilizer? I mean, you're basically there. Let's begin with an example. Let's look at the 1-qubit example. Yeah, we have the eigenstate of X. What is the stabilizer group? I mean, what elements does it have? What is the group structure? So we have two elements and that property. So we have a two-element group. And we have the property that you just mentioned, that the non-trivial element squares to the identity. So that group is Z2. Yeah? And so if we have a larger stabilizer group, we have other elements that they commute, so the order doesn't make a difference, and they still square to the identity. So if we have n qubits, then the stabilizer group, the maximal stabilizer group, is Z2 to the power n, and that is a finite group. In the stabilizer scenario, everything is finite. So there is certain unitaries that go well with stabilizer states, and here's the definition. It seems you're still thinking about the stabilizer group. Huh? Yeah? Okay, good. Okay, so the Clifford unitaries. So an n-qubit Clifford unitary first is a unitary in SU2 to the n. So that's the biggest group we'll consider for n qubits, the special unitary group, and now we are considering a subgroup thereof. The Clifford group is a subgroup. Okay, so it is these Clifford unitaries, they are all elements of SU2 to the n that do something to Pauli operators. Namely, you take any such Clifford unitary and conjugate any Pauli operator. And the result of this is going to be another Pauli operator, or itself, it's going to be a Pauli operator. So what Clifford unitaries do is that they map Pauli operators onto Pauli operators under conjugation. Good, so maybe, I don't know if you've ever come across such a property, but yeah, so that is a very useful property. So for example, so you remember the Hadamard gate, yeah? We had the Hadamard gate in the universal set. Maybe you have a little bit of familiarity with the Hadamard gate. So do you know what happens if you conjugate the Pauli operator, say, Z, under the Hadamard gate? Any ideas? Had anybody done the calculation yet? Yes? You get an X. You get an X. Now, if you conjugate that X again, what do you get? Z, because the Hadamard squares to the identity, exactly. And therefore, so same for Y. Yeah, so the Hadamard maps Y into minus Y, which is a consequence of what you just said. Okay, so it is precisely of the Clifford type. It maps all Pauli operators into Pauli operators. So you see, some gates that you've already seen have this property. And so there is an immediate consequence of this definition, and that consequence is stabilizer states are mapped onto stabilizer states under the application of Clifford unitaries. Okay, let's just quickly see why this is so. All right, so the question is, given a stabilizer state psi, what is the stabilizer of psi with the application of some Clifford unitary? Yeah, so CLN, this is our notation here for Clifford unitary on n qubits. Okay, so let's see what this is. Yeah, so we have psi is G psi, where G is in our stabilizer. And so now we can make, so kind of looking what we get, so we want to invoke a state U psi, so we can insert an identity here in the form U dagger U. That's just the identity by definition of unitarity. Okay, so now I have a state U psi here. If I want to, but on the left-hand side, I still have psi. So what I now do is I take this equation and multiply it with U from the left. So what I then get is U psi, which is the state that I want to reason about, is, again, I'm multiplying from the left, UG U dagger U psi. Yeah, okay, and what I really care about is this part. Okay, so we find, okay, so we're done. Yeah, so we have now a stabilizer relation for the transformed state U psi. Okay? Okay, you have it right here. So, so G, so any G in our stabilizer, G is mapped to UG U dagger. Okay? Okay, so it's conjugated. And so now you can look at it more closely and you will find that conjugation by unitary preserves all your goodies, all the properties that we previously had, hermiticity, abelianness, group structure, you name it. All of this is preserved under under conjugation. And so the stabilizer that you had is updated into a stabilizer, into a new stabilizer for the new state, which is just the old stabilizer element-wise conjugated under this unitary U. Good, so that was the upshot here. Clifford unitaries take stabilizer states into stabilizer states. We talk about the C-NOT gate. The C-NOT gate is the entangling gate that previously occurred in the universal set. So it is this thing. So we have a control qubit C and a target qubit T, and the state of the target qubit is flipped or not depending on the state of the control. Yeah, okay, so that's the C-NOT gate, and we apply it to a product state. So we have two qubits sitting there. One is in the state plus, and the other is in the state 0, tensor product state. Okay, so if we apply the C-NOT gate to this state, and it's easy to see that you get a Bell state. And let's arrive at the same conclusion in the stabilizer formalism. So that was very fast. Here the stabilizer formalism will be not as fast. You will have to do something. And yeah, if you go to larger problems, then you'll suddenly see the efficiency of the stabilizer formalism. But before we do that, let's practice it in small examples. You can do something here. Okay, I help you a little bit. I help you with the easy part though. So this is our initial state plus tensor 0. So here is the stabilizer relations that describe this state. Yeah? So X on the control is in the stabilizer of that state, and Z on the target is in the stabilizer of that state. So what we saw earlier is that under a Clifford operation, the stabilizer is conjugated. So now, yeah, stabilizer generators right here, they are conjugated under the C-NOT. So let's calculate what this gives us. So here you have the x on the control conjugated under the C naught. Yeah? So, so let's calculate that. Can you help me with that? So we have the C naught with the control and the target is 0, 0 on the control times the identity on the target plus 1 on the control tensor the spin flip sigma x on the target. And what we want to conjugate is x on the control. Good. So let me write this a little bit better. So x goes into C naught xc C naught dagger. And what is that? There is any number of ways you can do it. So the way I have done it here is, first I recognize that the C naught gate is Hermitian, so one can leave out the dagger. And then the way I did it, I exchanged the order of this and that. They are not commuting, but if you propagate this x here backwards, you change a 1 into a 0 and a 0 into a 1. And so now it takes this form, and so on and so forth. There's many ways of doing it. And some of you have arrived at this conclusion. So the upshot is the x on the control maps to the tensor product of x's on both qubits. So this was for one element in the stabilizer. Now for the other, we are not going to do this. So the z on the target is a similar calculation that shows also the z on the target maps to the tensor product of both z's on the control and the target. Okay, so these are the propagation, two of the propagation relations. You there did another. You did the x on the target, and you found that x on the target remains the x on the target. The same is true, in fact, for the z on the control. It remains the z on the control, but we don't need that for the present exercise. But if you ever do something in fault tolerance, quantum error correction, I mean, you'll know these propagation relations in and out. Yes. So where was I? Okay, so that's the update. And so these operators is what our stabilizer generators are updated to. And yeah, so they define a Bell state, which is consistent with what we had already found by direct calculation. Good, so here the stabilizer formalism was actually much harder than doing it directly, but when you look at larger problems with more qubits, then the order reverses. Then you'll find that stabilizer formalism becomes very efficient. Good. Okay, so this was an example for Clifford unitaries, and there is one more thing that we have to look at, and this is the update under Pauli measurement or Pauli measurements. So, so consider a Hermitian Pauli operator. We said earlier we have all these phases, but now the phases are adjusted such that the Pauli operator is Hermitian. And with this phase convention, then we can talk about what a Pauli measurement is, and as we discussed earlier, and so now all the work we had spent on defining the measurement process pays off. So we know that measurements are described by sets of projectors. This is a two-outcome measurement. So we have two projectors, one for outcome plus, that is positive eigenvalue, and one for outcome minus, the negative eigenvalue. And these these projectors look like this in terms of the Pauli observable P measured. Yeah, so an immediate consequence of this, and this is what we will subsequently show, is that stabilizer states are mapped onto stabilizer states under Pauli measurement. So when you do a Pauli measurement and have a stabilizer state to begin with, the family of stabilizer states is not left. You map to a stabilizer state, possibly the same, possibly another. Okay, so this is what we want to establish very soon. It's the next thing to establish. And then we can now draw a bigger conclusion, looking at the stabilizer states, at Clifford unitaries, and Pauli measurements. So what we now conclude is that these three elements together form a closed subtheory of quantum mechanics. Yeah, so we have a stabilizer state to begin with. We observe that under Clifford unitaries, that property is preserved. Yeah? We will end up in a stabilizer state after any Clifford unitary, given we started in a stabilizer state. And Pauli measurements do the same. They map us from a stabilizer state to a stabilizer state. So we never leave the realm of stabilizer states if we only apply Clifford unitaries and Pauli measurements. So that makes it a closed subtheory of quantum mechanics. It is a subtheory because it has finitely many states, finitely many unitaries, and finitely many measurements in it. Yeah? So it's a finite object. So it is therefore it is restricted in its scope. But the good thing about it, and this is what we'll elaborate on, is when it applies, it can be efficiently followed. It can be efficiently classically simulated what's happening. So that's the green point down here. Okay, so update under Pauli measurement is a little bit more complicated than what we saw for the unitaries, but this is what we are now going to look at. Okay, so let's get started with that. So the first point to make is that after a measurement of the Pauli observable P, plus or minus P, depending on what the outcome was, is in the stabilizer. Okay? So here is your projector again. So this thing represents measurement. Yeah? So if you have, so this sign here, this plus minus, encodes the measurement outcome, positive eigenvalue, negative eigenvalue. Or maybe I should have said more about this. I mean, if you like, you can show that these are projectors. I mean, they are obviously Hermitian, but they're also squared to themselves. So that's a property that you need for a projector. And if you multiply them, you get zero. Maybe so this is what we required for projectors that are being used in measurement. Okay, so just wanted to say this on the side. You can verify this for yourself if you want to. Yeah, it has to be satisfied. Good. Okay, so now we want to show that, so this is the post-measurement state up to normalization, and we want to show that it is an eigenstate of the measured observable. Okay, so let's see if we can do that. So first item is just associativity of multiplication. Oh, wrong color, it seems. So first thing is we just put the brackets differently. Yeah, everything is associative here. Okay, so now we have to multiply this Pauli observable here to this projector. Okay, and P times I, obviously P, is obviously P, and so P times P, as we observed earlier, P squared is the identity. So we're getting basically what we had. In fact, if we had a minus, we get minus the projector, and if we had a plus here, we get exactly the projector back when we multiply by P. Good, so this is simply plus minus I plus minus P over 2 psi. Good, so you now see that we have the same quantum state, namely the state after projection. So this is the action of the measurement on the state before measurement. This gives you the state after measurement. It's the Dirac projection postulate. Okay, so we find that the resulting state here is an eigenstate of the measured observable with the eigenvalue that you find here in the corresponding projector. Okay, so summarize again. After measurement of a Pauli observable, that observable or minus itself, depending on the measurement outcome, is going to be in the stabilizer. Yeah? Okay, so our question now is, how is the stabilizer updated under a Pauli measurement? So we have just answered part of the question, namely the measured Pauli observable, either itself or minus of it, becomes an element in the stabilizer, but that's certainly not the whole stabilizer, so we need to figure out about the rest. Okay, good. And so there is two cases that we now need to consider. The first case is that P, the observable that we measured, or the negative of it, was in the stabilizer before the measurement, or that it was not. Yeah, and so let's begin with a case where the observable that we measure, or minus itself, was in the stabilizer before measurement. So then the stabilizer is in fact unchanged, because we know that the stabilizer is an abelian group that we have established. And so now, since P modulo sign is in the stabilizer, it commutes with everything else in the stabilizer. So these properties persist. Yeah? So every element that was in the stabilizer before the measurement will remain in the stabilizer after measurement. So that is the case whenever the Pauli observable that we measure is already in the stabilizer. So, okay. So that was the first case. Now comes the more complicated case. So let's now assume that P is not in the stabilizer, or minus P, I mean both P and minus P are not in the stabilizer before the measurement. Okay, so then there is two subcases. Now we look at all the elements in the stabilizer before the measurement, and some will commute with P, with the observable that I measure, and some will anti-commute. Okay? And yeah, so those that commute will remain in the stabilizer, so this is completely like the above. Yeah? So now we need to talk about what happens with elements in the stabilizer before measurement that anti-commute with the measured observable. Okay, so let's look at that case. So yeah, so first, so this psi here is the state before measurement, and when Q is in the stabilizer, this means its expectation value is +1, yeah? Psi is an eigenstate of Q with eigenvalue 1, so it's just absorbed. Normalization condition tells us that this is 1. And now let's look, for comparison, let's look at the post-measurement state. So let's look at psi let me check how I did it. Psi I plus minus P Q I plus minus P. Okay, so this is modulo norm, the state after measurement. Okay, and Q was in the stabilizer. So what we do is we propagate it in here and absorb it. But now comes the anti-commutation property. Yeah, so when I exchange the order of Q and P, I get a minus sign because they anti-commute by assumption. And so what's going to happen here is the change of this relative sign. So what I'm getting is this. Yeah, that relative sign has changed. Q psi. Okay, and so I can run the Q in here because it's a stabilizer, so it will disappear in this way. But now I have two projectors here corresponding to opposite outcomes. And the product of these projectors will be 0. Yeah, so that's by definition of measurement. And you can also explicitly calculate it. And so this inner product here is 0. Yeah, and that's not supposed to happen for a stabilizer element. So this tells us that Q is removed from the stabilizer. Yeah? So that was the condition here, anti-commuting. So the elements in the former stabilizer that anti-commute with the measured observable, they are removed from the stabilizer. Good. So now we sum this up. We have learned two things. So the thing we have just learned is that elements in the stabilizer that anti-commute with the measured observable, with the measured Pauli observable, are removed from the stabilizer. What we had learned earlier, the first thing that we discussed, is that the Pauli observable that we measure itself becomes, depending on what outcome we get, it becomes an element of the stabilizer itself. So we lose stabilizer elements and we gain new stabilizer elements. And so the answer is the following. So what you see here is the stabilizer after measurement. And it consists of the part of the stabilizer that commutes with a measured observable, so that is defined down here, and I should say plus minus, but only one of those. Maybe I should write that too. Only one sign. Outcome. Okay, good. So yeah, so these parts are in the stabilizer, but just these parts, the commuting part of the old stabilizer, well, this is by itself a group, and P is just an element, the Pauli elements, and so you need to make this a group, and so you have here, and that's what the angular brackets represent. Yeah, you have the group that is generated by these pieces. Okay, so this is going to be your new stabilizer. Okay, so this is a little bit more complicated than the update under Clifford unitaries, but as we shall see, it's still computationally efficient. And there's one thing that I didn't show. Maybe you can show this for yourself in the bus, or for example, when you have a bit of time. So when we were going from the stabilizer before measurement S to the stabilizer S prime after the measurement, we were losing part of the old stabilizer, namely the anti-commuting part, and we were gaining something new. And so now the question is, do they balance out or not? And they do balance out. Yeah? So the new stabilizer S prime will be maximal if the earlier stabilizer was. Good. So that I didn't show here. You can show it for yourself if you like. And so this is the update of the stabilizer of a stabilizer state under Pauli measurement. So I have 5 minutes left and 5% of charge, coincidentally. So let's see if in those 5 minutes and 5% of electricity we get through the example. Yeah? So like in the previous case of the Clifford unitaries, we want to we want to verify this or illustrate this in an example. So the example is the following thing. So we have a 2-qubit stabilizer state. So qubit in state plus for qubit 1 and state plus also on qubit 2. So this is an eigenstate of x1 and simultaneously an eigenstate of x2. Okay, in that state, we measure the correlated observable Z1 tensor Z2. So it's a non-local operation, and we assume that we got the outcome plus. And so the question is, what state results from that operation? So we do this in the standard formalism, and indeed, again, it's a simpler calculation. So here's our projector, for outcome plus, identity plus, Pauli observable divided by 2 applied to this state. Okay, so to facilitate that calculation, what we do with this state, we expand it in the computational basis. I mean, the question that I asked at the very beginning, how many terms will this expansion have? You gave me the answer, 2 to the n. N is 2 in this case, so I get 4 terms, and here they are. 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. Okay? And now I'm applying this projector to either one of those 4 terms. First term, Pauli, the identity obviously gives the state back. This Pauli operator also gives the state back with phase plus 1. So these phases add up. Term survives. 0, 1. Okay, so the identity gives this thing back exactly. This guy, the Pauli operator applied to this, gives this state 0, 1 back, but with a phase of minus 1. So the phase plus 1 from here and the phase minus 1 from here, they cancel out. So the term goes away. Same thing with the state 1, 0 goes away, but again, the state 1, 1 remains like the state 0, 0 did. Okay. So this is what I remain with, and up to normalization, this is just the Bell state. Yeah? Okay, so that's the calculation in the standard formalism, and now we want to do this calculation in the stabilizer calculus, according to the rules that we have set up. Okay, good. So I said this already, so let's go back. So we start with this state. It is stabilized by x1 and it is stabilized by x2. Good. And so this means the stabilizer group for that state is generated by x1 and by x2. So this means that the stabilizer group, fully written out, has 4 elements, Z2 squared, 4 elements, namely the identity, x1, x2, and the product of x1 and x2. 4-element group. Okay, so now remember the measured observable is the tensor product Z1, tensor Z2. So I need to figure out the commuting part of that stabilizer. So the identity commutes with everything that's okay. For whatever that's worth, but okay, so now x1 anti-commutes with z1, z2. Yeah? Commutation on the second factor, anti-commutation on the first. Likewise, x2 anti-commutes with the measured observable. And x1, x2 commutes again, Anti-commutation on the first particle, anti-commutation on the second particle makes commutation over all. Good. So in this S-com, I retain 2 elements of the original stabilizer, namely the identity and this tensor product. And in our generator notation, I can write this as x1, x2. Angular bracket x1, x2. And so, remember that our new stabilizer is built from S-com, so this is x1, x2, and the measured observable, which was z1, z2. So that's going to be our new stabilizer, and that's consistent with the other picture. So that stabilizer stabilizes. Did I give that state a name? No, I did not. Stabilizes that thing. Yeah, you can verify this explicitly if you want to. Okay, so this is stabilizer update in a simple example, and the procedure is going to be always the same. The computational cost of this procedure we will look at later. And so my time is up, and so that's it for now. Maybe I can give you a little bit of an outlook of what we're going to do next time. And what we will be doing next time is identify Pauli operators with binary vectors. Yeah, I mean, maybe I say this is kind of easy. So in every Pauli operator, you can have the contribution x1, yes or no. It's a binary choice, binary answer. Likewise, z1, you can have it or not have it, binary choice. And you write all these binary choices for all the qubits as these exponents here. And so you can, you list all these exponents as a binary vector and modulo sign these exponents, this binary vector determines your Pauli observable P. And this is something we will be getting a lot of mileage out of. And so the Pauli operators P, they are mapped to binary vectors. And so all our stabilizer manipulations as a result of this will become linear algebra manipulations on rather compact matrices. And that we are looking at next time.